Yeah, in this video, I'm going to discuss about this valence bond theory. And the whole chapter of this chemical bonding has been described on my channel. And the details of this has been given in the description box below. Yeah, if you like it, please do like, share, and subscribe my channel. And coming back to the topic of this valence bond theory, to explain the chemical bonding, many more theories have been put forward before this theory, that is Lewis theory and Vesper theory. And because of the drawbacks of these two theories, this valence bond theory has been put forward in order to explain this chemical bonding. These two theories had their own limitations and unable to explain the formation of the chemical bond totally. So the valence bond theory has been introduced. And according to this valence bond theory, the covalent bond is formed by the overlap of the atomic orbitals of the atoms. So here the new concept of the atomic orbitals have been introduced, where he said that this Pauling in 1954, he said that because of the overlap of these atomic orbitals, this covalent bond has been formed. See, this orbital is nothing but the probability of finding the electrons around this uh, nucleus. So, because of this overlapping of this atomic orbital, which are of the two atoms which are involved in the bonding, for example, when you take this hydrogen and the two hydrogens, I mean, the formation of this hydrogen molecule here, the two hydrogens involved in the bonding, there is a uh, overlap of these atomic orbitals. So the orbitals are nothing but the probability of finding the electrons around the nucleus. So there's an overlap in between these two orbitals, which results in the formation of this covalent bond. So as a result of this overlapping of these atomic orbitals, the covalent bond is being formed. And the total theory is based on this overlapping of these atomic orbitals. Yes, and when we look at the postulates, so the main postulates of this valence bond theory, so as I said, the covalent bond is formed because of the overlapping of the atomic orbitals. And what is the main concept is, when we take, for example, the H2, the same H2, we know that the electronic configuration, only single electron, this hydrogen, so it is 1s1. When we take this orbital of two hydrogens, they are only single electron which is present, which means that they're half filled. So the valence orbitals here should be half filled. Only then it can accept another electron. So only then it can accept another electron. So if they are fully filled, these orbitals, so it doesn't accept an electron because they are fully filled. There is no point in taking electron into this. And yeah, where do you think it will take this electron and place it if it is fully filled? So only the half filled orbitals are, which are in, I mean, the half filled atomic orbitals which are present in the valence shell are participating in the formation of this covalent bond, and these two orbitals, I mean the valence orbitals participating in the formation of the covalent bond, should be of opposite spin. Only then they can form the covalent bond. Yeah, the Pauli's exclusion principle says that no two electrons in the orbital will have the same quantum number. So in order that they should have the quantum numbers different, that is all the quantum numbers, they will have the opposite spin here. K, L, M, and all this should be different. That means all these quantum numbers should be different. Only then it can, only the two electrons which are present in the atomic orbital should have all these principal quantum numbers different. So this the spin should also be opposite in order that they will form the covalent bond. As a result of this, the hydrogen molecule which is formed will be fully filled now with the two electrons which are having the opposite spin here. This is the main point to be remembered while reading the postulates of this valence bond theory. In short form, it is also called as VBT, valence bond theory, opposite spin. Right. So the main point is they should be, the combining orbital should be half filled with the opposite spin. And only the orbitals of the valence shell will be taking part in this formation of this covalent bond. And so during the formation of this covalent bond, yes, When we look at the example of again this hydrogens here, when they're far away, there is no attraction. So we know that. But as they come nearer to each other, these two atoms, as atomic orbitals are approaching each other at certain minimum distance, this bond is formed, that is a covalent bond, and the distance at which this is formed is nothing but the distance in between the two nuclei. This is the interatomic distance, which is nothing but the, so this distance is called the interatomic distance, which is nothing but the bond length. So bond length is nothing but the distance in between the nuclei of the centers of the nuclei of the two atoms. And the energy which is associated with the formation of this is the bond energy. So uh, so we can describe this energy as the energy which is released when this particular molecule is being formed. In the case of the hydrogen, when we look at it, it is around, yeah, 1.47 into 10 to the power of minus 19 joules. So it is not 1.47 into 10 to the power of minus 19 joules for hydrogen molecule. So this is minus because this much of energy is released, an exothermic reaction when the bond is being formed. So this much of energy is released when hydrogen molecule is formed, or in other words, this much of energy is necessary in order to break the bond in between these two hydrogen atoms into their atoms here. So the bond energy here is nothing but the amount of the energy which is released when that particular molecule is formed. So the distance between these two is the minimum distance at which then they are stable here. So this the stable molecule at which the energy which is associated with this is minimum. And when they are approaching each other a little more than this interatomic distance, then there is a repulsion in between these two atoms. As a result, the molecules become unstable and the energy which is associated with this will be more. So there's an optimum distance at which the energy is minimum. That means the molecule is stable. So this is the energy. This is the nothing but the bond energy which is required. I mean, which is associated with this formation of this molecule. If they are brought closer than this, then there is a repulsion which is taking place in between these two atoms. This repulsion is nothing but the electrons of hydrogen 1 and hydrogen 2, and then there is a repulsion in between the electron of hydrogen 1 and hydrogen 2, and the nucleus also there is a repulsion. And so which means that the repulsion is dominating over the attraction in between these uh, atoms. So so this is the energy which is associated with the formation of this hydrogen molecule. Yes. And the main postulate of this valence bond theory, next main postulate is when the atomic orbitals are overlapping, the extent of the overlap is proportional to the strength of the bond. The more the overlap, the stronger is the bond. In other words, strength of the bond. Yes, the more the overlap, the stronger is the bond. If the overlap is less, then the overlap is less here, then the bond will be weaker. So we can say that the extent of the overlap is directly proportional to the strength of the bond here. Yes, and which is directly, in other words, we can say that the strength of the bond is directly proportional to the bond energy, which inversely proportional to the bond length. If the bond is stronger, the energy which is associated with it is also more, and the distance in between the atoms will be more if the bond is weaker. So it's inversely proportional to the bond energy. The bond length is inversely proportional to the bond energy. If the bond energy is more, the bond length is small, and if the bond energy is less, the bond length will be more. So this is about the postulates of this valence bond theory. And when we come to this type of overlapping, there are two types of overlapping, sigma and pi. So sigma is nothing but the head to head overlap, which means that they're overlapping along the internuclear axis. So this is the nucleus of this s orbital in both these cases. They're overlapping in such a way that the uh, electron density is in between these two nuclei. This is called as head-on head overlap. And the pi bond, I mean, the next one is the lateral overlap, where the overlapping takes place in such a way that laterally, for example, when we take here the sigma bond plus another p orbital, this is the p orbitals, will result in the formation of, yeah, this type of bond. Yes. But if they're overlapping parallelly, in this case, that means laterally, the overlapping takes place in this way. Yes, if the p orbitals overlap laterally, then that type of overlapping results in the formation of this pi bond. And the head on overlap will result in the formation of this sigma bond. So, where the distance, I mean, the electron density in this uh, head on overlapping will be in between the two nucleus, whereas the electron density in the case of the pi bond formation will be above and below the internuclear axis. This is the internuclear axis. That means the uh, yes, the electron density will be above and below the internuclear axis in this case, but in this case it is in between the two nucleus. And this head-on overlapping is stronger than that of this lateral overlapping, which means the sigma bond is stronger than that of this pi bond. So these two types of bonds have been introduced in the valence bond theory. So when we come to this sigma bond, let's look at this in detail now. Yes. When we take this, for example, the same hydrogen atom, uh, formation of this hydrogen molecule. So the hydrogen's atoms are, when we take this, one electron in this case, and the other electron with the opposite spin in the other hydrogen atom. This is 1s orbital in both these cases. This orbital is spherical in shape, we know that. And when these two atoms, I mean, atomic orbitals are overlapping, results in the formation of this hydrogen molecule with the two electrons which are having the opposite spin. Yes. And these two electrons have been concentrated, I mean, the electron density in this case is concentrated in between the two nuclei in this case. So this is the formation of this LSS overlap, that is SS sigma bond, is formed in the formation of this hydrogen molecule in between the two hydrogen atoms. And when we come to this other type of overlap in sigma bond, that is the sp overlap. For example, when we look at the formation of this HCl, the H, we know that the electronic configuration, only one atomic number, it is 1s1. So this s orbital is involved in the bonding with a single electron in this case. And when we come to this chlorine, it is 17, the atomic number, and the electronic configuration is 1s2, 2s2, 2p6, 3s2, and 3p5. So the valence shell is 3s2, 3p5. So when we, this is 3s, 3p5, this is with the opposite spin here. So this is 3s and 3p here. So the 3p, for convention, we can write this, uh, yes. Yes. Now we can write it as 3px. Yes. This is 3py and 3pz. So this 3pz, in which case now we can write this I mean, we can name them px, py, and pz. It's okay. Any of them we can be named px, py, and z. But for convention, we take this the last orbital as pz here. So this 3pz orbital with the opposite spin will overlap with this s orbital of hydrogen atom, resulting in the formation of this HCl. So here, one s orbital of hydrogen atom, which is symmetrical, that is spherical in shape, will overlap with the 3p orbital, that is in this case the 3pz. Just for convention we are using this, with the opposite spin here, will resulting in the formation of this HCl molecule, where s orbital of hydrogen is overlapping with the p orbital of this chlorine atom, resulting in the formation of this HCl covalent bond. In between this H and Cl is being formed. So when we look at the HCl configuration here, we have 3s, which is already fully filled, and now we'll have these three orbitals, which were half filled in hydrogen and chlorine initially, now becomes fully formed and will attain the stable electronic configuration. The main concept of this valence bond theory is the pairing up of these electrons will occur, the half filled electronic configuration, which were initially half filled, after the formation of the covalent bond will become fully filled. Now they are in other words, the pairing will occur fully filled, the half filled will become fully filled, and the unpaired electrons will become paired up now. Paired up, resulting in the stable electronic configuration. So this is the type of a sigma bond where HCl sigma bond is being formed in between the s and the p orbital of hydrogen and chlorine respectively. And now look at the another type of sigma bond formation, that is now the pp overlap. So in this pp overlap, for example, when we take this F2 here, that's fluorine, two fluorines in this case. So we know that the fluorine is 9 atomic number. So electronic configuration will be 1 is 2, 2 is 2, 2p5. Right? So another one is also the same electronic configuration, where the outermost electronic configuration in this will be 7. Now this is 2s and this is 2p now. This one, yes, half filled. And now when we look at the electronic configuration of other fluorine, it will also have this 2p5. One of the orbitals is half filled in both these cases, but the electron in this valence orbital will be of the opposite spin. So these two, that is, this is 2s and 2p, that is 2pz orbital will now overlap. The p orbitals of these two will overlap, resulting in the formation of this pp overlap, that is sigma bond is being formed by the overlap of these pp orbitals, resulting in the formation of this F2 molecule with a pair of electrons which are fully filled now. The pairing up of the electrons will occur, which were initially half filled will become fully filled, resulting in the formation of this fluorine molecule. These are the examples of, yes, when we look at them, to summarize, so this is the formation of the sigma bond. There are three types of sigma bonds, that is SS overlap, sp overlap, and pp overlap, where in SS overlap, s orbitals are involved in the bonding. Example is hydrogen. And in the sp, we have HCl or HF or HBr, where S of hydrogen is overlapping with the p orbital of this chlorine here. Yes. Here, the s orbital of this hydrogen will overlap with the p orbital of this halogen here. In the case of HCl, the p orbital of this chlorine, that is uh, 3p orbital, and in the case of fluorine it is 2p, and in the Br it is 4p orbitals which are involved in the bonding here. So in the case of pp overlap, the examples are fluorine, where pp and the p orbital of one fluorine is overlapping with the 2p orbital of other fluorine, and also in the Cl2 it is 3p, and Br2 it is 4p, which is involved in the overlapping here. Yes, this is the formation of the sigma bonds. Now look at the formation of this. Yeah, I've already discussed this. In the case of pi bond here, the only the p orbitals are involved here in the formation of these pi bonds, and s orbitals are not involved, where that a lateral overlap will occur, resulting in the formation of uh, pi bond here, where the electron density is distributed above and below the internuclear axis. This is the formation of this pi bond where the p orbitals are involved. Yes. Now looking at the differences in between these two here. So now look at the formation of this multiple bonds, that is double and triple bonds, according to this valence bond theory. Yes, when the formation of this oxygen molecule, the two oxygens which are involved in the bonding, the electronic configuration, this oxygen, we know that it is 8, 1 is 2, 2 is 2, and 2p4. So there are two unpaired electrons which are present in each of these two oxygen atoms, where one of the p orbitals, for convention, this is 2p5 and this 2pz. So 2py, for example, is involved in the formation of the pi bond, and this is involved in the formation of the sigma bond. So for example, when we take this oxygen, this 2p orbital, in this case the 3p orbitals are oriented in such a way that they are perpendicular to each other. So this is pz, px, and this is py. So this pz is involved in the formation of the sigma bond, so this is the sigma bond, and this px in this case, so this, let's take this as px here, this is 2py, right? 2py is fully filled, and now in this case this is 2px which is involved in the formation of this pi bond here. So this is the pi bond above and below the internuclear axis, and the sigma bond, the electrons are in uh, along this internuclear axis in this case. So now in the formation of this oxygen bond, so one is sigma bond and the other one is pi bond. So this pi bond is formed only after the formation of this sigma bond. So does not have this independent existence, this pi bond. So only pi bonds cannot be formed. They can be formed only after the formation of this sigma bond. Whereas sigma bond can exist independently, that means they can be formed without the formation of these pi bonds also. So this is the formation of this oxygen molecule, uh, yes, based on this valence bond theory. And when we look at the formation of this nitrogen molecule here, the nitrogen, we know that it is 7, so electronic configuration will be 1s2, 2s2, and 2p3. So here when we look at the valence configuration, it is 2s2 and 2p3, where 2p orbitals are half filled here in this case. So one of them will be involved in the formation of this sigma bond. For example, the same case, this 2px, 2p y, and 2pz here. So these two are involved in the formation of the sigma bond. This 2px and 2py and z are involved in the formation of this pi bonds here. So this is a sigma bond, and these two are the pi bonds above and below the internuclear axis. So in this nitrogen, which is a triple bond, one is the sigma bond and the other two in this case are pi bonds. So let me use another color pen here. This is pi and this is pi. Yes, these are the Yes, this is a formation of a triple bond in between the two nitrogens, where one is the sigma bond and other two are the pi bonds in this case. Yes. Now look at the differences in between this sigma bond and pi bond. So the main difference here is it is formed only by end-to-end overlap, and this is by lateral overlap. So this is, for example, when we take this p orbital, this is end-to-end overlap, and this is by means of this lateral overlap. Yes, and the orbitals which are involved in this are SS, SP, and PP. This is only PP orbitals. And it's a stronger bond, as I said, this is a stronger bond because it's a head-on, head-to-end, end-to-end overlap or head-to-head. This is only a lateral overlap, so it's a weaker bond. And yeah, this is electron cloud is symmetrical about the joining of two nuclei because it is distributed in between the two nuclei along the internuclear axis. But here, the electron cloud is distributed above and below the internuclear axis, so it is not symmetrical along the internuclear axis. Yes, and it consists of yeah, I said this, and the free rotation about the sigma bond is possible. So when we take this, this is the internuclear axis, right? So if we keep this stable, I mean as it is, and if you rotate it along the internuclear axis, it doesn't change, right? It doesn't change the formation of the sigma bond, so the free rotation is possible. But in this case, in the case of this lateral overlap here, when we keep one atom still like this and try to rotate the other, so this is not possible. So rotation is restricted in case of p orbitals or pi bonds. So this is what it means. Yes, let's look at the formation of a few molecules based on this valence bond theory. When we take, for example, the formation of this hydrogen fluoride, this H is 1 is 1. So single electron with unpaired electron, I mean single orbital. And when we look at this fluorine, it's 9 here. So 1s2, 2s2, and 2p5, right? Yes. So 1s2 is completely filled, 2s2 is also filled. So 1 is 2s, and this is 2p. Yes, this is one of the orbitals in this p is half filled with the opposite spin in this case, where s of this overlapping with the 2p z orbitals of fluorine, resulting in the formation of this HF bond, where the sp overlapping is taking place, resulting in the formation of this HF molecule. Yes, when we write the formation of this HF here, it becomes 1s2, 2s2, and yes, 2p 6 here, where the overlapping, I mean the half filled orbital will now become completely filled in HF molecule. And let's look at the formation of H2O also in this case. So again, the oxygen is 8 here, so it is 1s2, 2s2, and 2p4. So 1s2, 2s2, and 2p4 here. 1s2, 2s2, 2p4 here. 2 are half filled, and we take this hydrogen atom and one more hydrogen atom here. These are also half filled with opposite spin. So the 1s orbital of this will overlap with the 2px of one orbital and 2py of another orbital, resulting in the formation of this water molecule here. Yes. So this one, yes. Yes, this hydrogen and yes, resulting in the formation of sp overlapping. Here 2sp overlapping is possible, so this is the formation of with the opposite spins in these two cases, and two sigma bonds are being formed here between the hydrogen and oxygens here. Yes. And let's look at the formation of this methane now. Uh, CH4, in this case also the carbon is C6, and so one is 2s2 and 2p2. One is 2s and 2p here. So when we observe this carefully here, there are four hydrogen atoms. This hydrogen is one, so only one is one. So only two hydrogens can form bond with this carbon atom, because there are only two unpaired electrons here. Two unpaired electrons, only two half filled. Two unpaired electrons are only two orbitals which are half filled. So in order to overcome this, he said that the excitation is possible of this valence electrons if the bond is necessary to be formed. So we can now excite this one of the electrons from the 2s orbital to the 2p orbital. Now these are of the same quantum number. This is a 2 of the same principal quantum number, that is they excited from 2s to 2p in this case, where one of the electrons from 2s orbital is excited to 2p orbital. As a result of this, now this carbon atom will have, this is of 1s and 2s1 an unpaired electron, and as a result of this excitation, this 2p orbital, will have four unpaired electrons in the valence shell. That means all these 2s and 2p are half filled. Now four unpaired electrons are present. Now these four unpaired electrons which are present in the valence orbital when can form the bonds with four other hydrogen atoms here, having this one unpaired electron which is opposite spin, resulting in the formation of CH4 molecule. But when we observe here, the bond angle in this case, CH4 is 109.28 in the CH4, and bond angle in ammonia is 107, and in water it is 104 around, and all these bonds are equivalent. So when you observed here, this one of the bonds is in between s and s orbital of this is of carbon and this is of hydrogen, and the other one in between the s and p, and the other of sp, and other is also sp. So one is of one type and the other three of one type. So but when we look at it experimentally, it has been said that all the four bonds are equivalent. But according to this, all the four bonds should not be equivalent, and there should be certain characters which should be different in between the formation of these four bonds. But this could not be explained based on this theory. So the hybridization has been introduced in order to overcome these shortcomings. So I'm going to discuss about this hybridization in my next video.